So now let's have a look at what a competition subsystem has to do step by step. You can identify a number of different parts to its behavioral selection role. First, it has to assign to each receptive field a set of recommendation weights in favor of a range of different behaviors. Each behavior will have a different weight. At each point in time, the subsystem has to determine the total recommendation weight in favor of each behavior across all the currently detected receptive fields. Then it needs to select and implement the behavior with the largest total recommendation weight. In most circumstances, it's important that at least one behavior is selected. And it's also important that the selection be clean. In other words, the subsystem mustn't select two incompatible behaviors at the same time, like trying to move the same arm in two directions simultaneously. Although sometimes two compatible behaviors might be selected, like walking and chewing gum at the same time. Most people can do both at once. In a novel situation, the novelty could mean that there's no behavior with a strong recommendation weight. But often there's value in trying some behavior with perhaps a relatively weak recommendation strength experimentally so that you can learn the best behaviors for the new type of situation. And sometimes a behavior to make changes to recent recommendation weights is appropriate and needs to be selected. And of course, these reward behaviors will often be selected at the same time as other, perhaps motor or indirect activation behaviors. Then there's another factor that has to be taken into account. If a receptive field with a recommendation weight in favor of one particular behavior tended to be detected relatively often when that behavior was appropriate, then if the reward behaviors constantly increased its weight in favor of that behavior, that recommendation weight could get so large that the behavior would be selected whenever that one field was detected, even if there were quite a few other detected fields indicating that some different behavior was appropriate. So the growth of individual recommendation weights mustn't be excessive. So what we've got here is a list of detailed functions that the behavior selection subsystem has to carry out. So let's think about the types of algorithms that could achieve all that. As discussed earlier, the competition subsystem must have a range of components corresponding with different behaviors. And I've illustrated a number of components on different scales because I'm mostly going to think about just two of them. Each component will get inputs from a range of receptive fields. And to ensure that only one behavior is selected, some overlay regulation by internal structures is going to be required. One substructure will have to assign a different weight to each input, this weight being the recommendation weight of the receptive field in favor of the component behavior, and those weights will have to be adjustable. An output from the component will be a command to perform the behavior. So the internal structure has to make sure that only one component produces an output. One way to do this is for all the top subcomponents in each component to produce an output proportional to the total current active recommendation weights in favor of that behavior. This output excites the middle subcomponent in the same component. But that same output also inhibits the middle subcomponent in all the other components. And its own middle subcomponent also gets inhibition from all the other components, just as I've illustrated. Both get inhibition from all the other components. So each middle subcomponent gets excitatory inputs from within the same component and inhibitory inputs from all the others. And this establishes a competition between the alternative behaviors. But it doesn't actually guarantee that one and only one behavior will be selected. There could be several components left with an output, or the inhibition could eliminate outputs from all of them. So you need another layer of regulation to ensure that one and only one behavior is selected most of the time, such as the mechanism I'm going to illustrate. In this mechanism, an external subsystem gets excitatory inputs from all the middle subcomponents. It sends inhibitory signals back to all the output subcomponents. So if the total middle subcomponent activity provided to that external subsystem indicates that more than one behavior is likely to be selected, the subsystem damps down all the component outputs to ensure there's only one. So we can expect to see some structures implementing algorithms vaguely like this somewhere in the brain.